So we're going to define electric potential energy, PE, but in this unit it'll be electric, not gravitational. Very similarly, Alexis, to gravitational or orbital gravitational potential energy. We're going to say that it reflects the work that must be done to move a negative charge, little q, from a point near the positive charge, big Q, out to infinity. So we're going to imagine that this one is positive and this one is negative. Which way does Q want to, I'll use air quotes, fall? Which way does little q want to move? Okay, so we would have to do work, we would have to expend energy to pull it out all the way out to infinity, because it would be resisting us the whole way. Or, if the charges are like charges, pause for a second, but we have a bit of a problem. Stuff doesn't always fall down. What if the charges are like charges? Like charges. And so if the charges are like charges, it would be the work required to start out at infinity and slowly push, 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 and the closer you get, the bigger the force of resistance. Because like charges repel. Also recall that this is the force between electric charges, but because it varies with distance, we can't use force times distance. We have to use the calculus trick, and I'm just going to give you the punchline. Potential energy is little k, Q1, Q2, or I usually go with big Q, little q, over r, not r squared. Sorry? Almost the same. There's one thing that's missing here that showed up, and I had to do a long rant as to why it showed up in the gravitational potential energy equation. There's the negative in that one. Why isn't there a negative here? Because we're going to include the signs here. Look at your formula sheet. Did I put absolute value symbols around the Q's in the potential energy equation? No, no. Scalars, this is a scalar. What I used to tell kids is scalars include signs, because for the provincial they had to memorize this. I wasn't allowed to put the absolute value symbols around some and leave them off around the others. I just left them all as is. You had to realize which ones you put the signs in and which ones you don't. But if they're unlike charges what, everyone? I would have a positive and a negative. I would end up with a negative answer. Just like gravity, the negative is a force of attraction, so it takes care of it. The positive and negatives take care of themselves. If they're like charges, I'll either have negative times negative, which is positive, or I'll positive times positive, which is positive. It's the opposite of the negative potential energy that we had with gravity, because it has energy, because if you let it go, it will fall up, which sounds, it will repel. Okay. Also, this is relative to zero at infinity. We did the same thing that we did with gravity. So where do you have no potential energy? All the way out at infinity, whether you're both positive, both negative, or opposites. That's where the 0 point is, because you're so far away, there's no electric field, so there's no force on you, so you won't fall or get repelled. By this relationship, unlike charges have negative potential energy, so the negative takes care of itself, unlike in gravity where we had to install the negative to get 0 out at infinity. And this does make sense because it takes work to separate the charges due to their attraction. It should be just like gravity. You do get a negative answer just like you do with gravity. Example 1. Find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters. Nice try, Mr. Dewick. 3 centimeters, how many meters? 0.03 meters. From a positive 120 microcoulomb charge. Then B says, write a work energy equation if the negative charge is moved out to infinity. We'll assume the charges start and end at rest. And then C says, find the work. I would probably just ask C, wouldn't walk you through A and B. But here's the procedure. Camille F., what does A want me to find? Which potential energy? Is this gravitational potential energy? No. Electric potential energy. Can you read to me the electric potential energy equation, the new one? Go ahead. What was K? 9 times 10 to the 9th. Big Q, this looks like the big planetary charge that's standing still, so I'll put that in. 120 times. What was micro? Yeah, worth committing to memory, at least for this unit, because you're going to get sick of looking it up, but it is on your sheet in that metric chart that I gave you. I include the sign negative 75 microcoulombs all over 0.03. Similar typing to gravity, but the numbers are nicer, so it's not quite as much, blisters on your thumbs. What do you get? You should all practice typing these in, of course, because one of the big issues on the test was getting the wrong answer with the right numbers. I get negative 2,700 joules. And typically, you'll get answers in the thousands-ish. Okay? Negative 2,700 joules. That's how much potential energy this system right here possesses. Okay. B. Other Camille, what does B want me to find? Or write? I'm going to write a work equation, not a conservation of energy equation. And the reason is I looked at part C. What does part C want me to find? Okay, so I'm going to write a work equation. If part C had said, find the speed or find the R, I'd probably try conservation of energy, G. But here it's going to be, the same work energy theorem as before. Work equals the change in potential plus the change in kinetic. Oh, what does it say we can assume? And? No, it says we can assume two things. The charges start and... That means I can get rid of that whole thing. Okay. I'm sort of done. You want to go further? Fine. What's changing anything? So this is actually going to be K, Q, little q over R final minus K, Q, little q over R initial. Ooh, where are we ending up? Right? Relative to 0 at infinity. Allie, what does C want me to... There's my work equation, I guess. What does C want me to find? Apparently, it's going to be negative the potential energy. Initial. Which I conveniently found in part what? A. It's going to be negative 2,700 joules. Allie, what's a negative? Which makes sense. What it's saying is, I will have to do work, I will have to add energy, I will have to expend some energy to pull this charge away because it wants to fall. So let me go back to the picture here. I would have to pull because it wants to move towards that charge. I'm having to give energy. How much energy will I need to give to get it all the way out to infinity? 2,700 joules. So as long as you're careful, Nick, the point is the signs will take care of themselves and you'll get answers that make physics sense. Okay? Really similar to gravity. What was that?
Sorry, so Nick responded.
Paying attention, what the paying attention condition? Yeah, okay. I'm hopeful. I always am optimistic. I pretend my students might be paying attention once in a while. Hey, Nick turned the page without me having to tell him to turn the page, and some of you still haven't figured that out, so that's good. Oh, by this relationship then, Like charges have positive potential energy when they're near each other, and they'll lose energy as they fall up. Oh yeah, of course they're losing energy because they're getting further and further away. The force is getting weaker and weaker and weaker and weaker. And I mean, work energy is still force times distance, but we can't use that because it's a changing force, but the concept still works. Okay. So I like example 2, I like example 2, I like example 2, except both example 1 and example 2, a little too easy. I might add a speed as well. I might give you a KE, either initial or final. Find the work, okay, required for an external agent. What do I mean by an external agent? I don't know, invisible leprechauns, invisible angels, something, whatever you want. Something to place a 2.5, oh, what is a lowercase m? When it's in front of a letter. Milli is 10 to the what? Okay, I'll just replace it with a 10 to the negative 3. Millicoulomb charge, 5 meters away from a fixed 1.75 millicoulomb charge. Oh, I even told you here, milli is 10 to the negative 3. So this one is like nailed to the ground. It's fixed in place. This will be my big Q. And I get, even though this one is larger, I'll pretend this is my big planetary charge. And what we're doing is we're starting out here and we're push harder, until we get to there. Why do we have to push? Because like charges repel. Okay. Assume that it's initially an infinite distance away. That's a win. Something going to be 0. Oh, and that it begins and ends at rest. That's a win. Something is going to be 0, which is why I like this question, but a little easy. I might not have you start out at infinity, say. Man, what does this want me to find? Work equals change in potential plus change in kinetic. Our old work energy theorem. This is why I told you when we did the energy unit, this is by far the most useful definition of work. It's also the biggest pain. I mean, it'd sure be nice to go force times distance or MGH or what, yeah. Why can't I do that? That's a win. What's change in anything? So this is going to be PE final minus PE initial. Are any of those 0? This became a lot nicer. You'll notice we're not doing, remember the rocketry ones where it was 15 lines or so? We're not getting into that too much. Work is going to be, I guess, little k, big Q, little q, or Q1, Q2 over our final. 9 times 10 to the 9th. These are bigger charges. So I'm expecting it's going to take a lot more work because instead of microcoulombs, they're milli, which is 1,000 times bigger. Although we're not getting that close, 5 meters versus 3 centimeters. So maybe not. I don't know. The fixed one, 1.75 times 10 to the negative 3. 2.5 times 10 to the negative 3. What if one of these had been negative? I would include the sign. What if they were both negative? I would include both signs. In fact, these could both be negative. I'll get the same answer because that would still be like charges, and like charges.
Oh.
I have no idea what we get here. 9 times 10 to the 9th, 1.75 times 10 to the negative 3 times 2.5 times 10 to the negative 3 divided by 5. What if I divided by 5 squared? What would that tell me? The force? What if well, first of all, syntax error. What did I do? Oh, the 3 didn't show up. Divided by 5. You get 7,875? Okay. If I had said find the force of attraction, or sorry, repulsion between these, it would be that in newtons. If you only had one charge and no squared, or with the squared, that would be electric field. I'd need one or the other. I could calculate how strong the electric field from one of the charges was. Anyways, 7,875 units. So again, how much energy would I need to expend to push a reluctant charge 5 meters away from this? That much, 7,875 joules. By the way, what happens when I let go of a 2.5 millicoulomb charge? Whee! It would go shooting back. It would start to accelerate and it would fall away. It would get repelled. It would change its speed and change its height along a yucky, curvy force. Conservation. Ooh, maybe. So again, for energy, a scalar, we're going to include the positive or negative in the equation, unlike forces and fields, both of which are vectors, where we decide the direction ahead of time by looking at the polarity. How did we decide the direction of forces? We use like charges. How did we decide the direction of the electric field? Who remembers? Which way a positive sitting at that specific location that you're telling me to look at, I imagine a little positive test charge right there, which way would it want to move if it could? Usually from positive to negative, but sometimes you don't have both of those on your screen, so it's which way a positive would want to move if it could. If there is no external agent pushing the charges around, no invisible leprechaun, no angel, well, then the energy of the system will be conserved because what you start with is what you finish with. You're not adding energy or taking it to the system or taking energy away from the system. I like example 3. Example 3 is a nice question. An electron is originally 2.5 times 10 to the negative 11th meters from a proton and at rest. It's released and moves directly towards the proton. Find its speed when it's 1 times 10 to the negative 11 meters from the proton. I'm going to argue, Camille, first of all, are these charges like or unlike? Are these two charges like or unlike? Unlike charges. I'm going to argue mathematically this is just like dropping an asteroid from outer space. Except not gravitational force, electric force. But I am going to say, look, is there a change in, I'll call it height, radius? Will there be a change in speed? Is there a yucky, curvy force? Did this question ask how much work? So don't be telling me work. This is conservation of energy. I'm going to start out by going KE initial plus PE initial, KE final plus PE final. What did I usually do next when I was doing conservation of energy? I asked myself something. Are any of these zero? Where would potential energy be zero? Only one place. Out at infinity. We didn't start there. If I wanted to make your life a little easier, I could have, but I did not. Where will kinetic energy be zero? Okay. What are we trying to find? Speed. Let's expand this a little bit. So I guess it's going to be K, big Q, little q over R initial equals a half little m V final squared plus K, big Q, little q over R final. I'm not going to try and get the V by itself. What I am going to do is get the half mv squared by itself. I'm going to minus this to this side. I'll get K, big Q, little q over R initial minus K, big Q, little q all over R final. That equals mv squared over 2, half mv squared. I'm going to crunch this and get a number, a single number on the left. Then I'll get the V by itself. Easier. Also, I think I might be able to do that ditto mark trick again, because it's going to be 9 times 10 to the 9th, big Q. It's a proton. Good. Some of you are cluing in. Oh, yeah, he gave us that. It's a proton. What's the charge on a proton? The elementary charge, 1.6 times 10 to the negative 19. Little q, it's an electron. No, it's not 1.6 times 10 to the negative 19. Can't be. That's impossible.
Negative.
Could be negative 1.6 times 10 to the negative 19. All over. I guess our initial is 2.5 times 10 to the negative 11. Then there's a minus sign. And then Prabnur, is it same thing times same thing times same thing? On the top? Let's do our little same thing times same thing times same thing on the top. All over. What's our final, Prab? That's going to be mv squared over 2. Okay, let's get to typing. I think these might actually work out kind of nice so that I'm not going to be having to track like 15 sig figs. 9 times 10 to the 9th times 1.6 times 10 to the negative 19 times negative 1.6. I include the negative because this is energy. Times 10 to the negative 19 divided by 2.5 times 10 to the negative 11. And I get... You get a negative 9.216 times 10 to the negative 18. Yep. Yeah. Okay. Negative 9.216. Negative 9.216 times 10 to the negative 18 minus... Same thing. I think all I got to do is change the 2.5 to a 1.0 and I'm good, right? Negative 2.304 times 10 to negative 17. That equals mv squared over 2. I notice I have a minus minus, which is a plus. So it's going to be negative 9.216 times 10 to the negative 18 minus answer button. I will get a positive answer, which is good because I hopefully want to get a positive speed. I get positive 1.3824 times 10 to the negative 17. Anybody else? 1.3824. How would I get the V by itself? Times by 2, divide by m square root. Okay, so V is going to be 2 times 1.3824 times 10 to the negative 17 divided by m. It's an electron. What is it? Square root. Times by 2, divide by 9.11 times 10 to the negative 31. I would panic for a second because that's faster than light, but then I would say, oh yeah, square root. And I get, it's going to be a pretty fast speed. These things are moving. I get 550899. I get that. I'm going to write that in scientific notation. 1, 2, 3, 4, 5, 6, 5.5 times 10 to the 6th meters per second. Okay. Some typing, but not as yucky numbers as with gravity. That 6.67 just gums everything up for yucky decimals. I would have no problem. Here we got the V, solve for V. I would have no problem asking you to solve for R or solve for R initial or R final. I would not get them by itself. I would get their expressions by themselves, turn the other side into a single number, and once I had done that, then I would get the R final or the R initial by itself. Example 4. How much potential energy does this possess? How many charges are there in this picture? Let's label them. Q1, Q2, Q3. Do yourself a favor and do that right away so that we know what we're talking about. How am I going to do this? I'm going to find how much potential energy is between 1 and 2. I'm going to find how much potential energy is between 3 and 2. I'll add them up. Potential energy between 1 and 2 is going to be K Q1 Q2 over R12. It's going to be 9 times 10 to the 9th Q1, 5 microcoulombs, so 5 times 10 to the negative 6. Q2, negative 1 microcoulomb, all over, what's R? Don't say 2. 0.02. Nine times 10 to the 9th, 5 microcoulombs, negative 1 microcoulombs, divided by 0.02. I got a typo. Nine times 10 to the 9th, 5 microcoulombs, negative 1 microcoulomb. Oh, that would have been awkward. Missed the negative in the micro. Do you get negative 2.25? Yes? Okay. Let's repeat that for charge 3 and charge 2. So the potential energy between charge 3 and 2, that's going to be KQ3 Q2 over R32. It's going to be 9 times 10 to the 9th. Q3 is negative 2 times 10 to the negative 6th. Negative 1 times 10 to the negative 6. All over 0.04. I think I can backspace and just change a few numbers here. Instead of a 5, it's going to be a negative 2. And instead of a 0.02 on the bottom, 0.04 on the bottom, I get positive 0.45? Yeah. How will I add these together? What? No. Why don't I need to go tip to tail? Which is looking for a word that starts with the letter S. It's a scalar. No need to do tip to tail. Would I have an answer where if you went tip to tail, would I have that to pick from? Probably. And you would have done a whole bunch of extra work for nothing. Potential energy is just going to be negative 2.25 plus 0.45. We're done. Negative 2.25 plus answer button, and we're done. The total energy that charge 1 possesses based on those 2 charges is negative 1.8 joules. What does that mean? If we go back to the original picture, if I wanted to pull this charge all the way out to infinity, how much energy would I need to add to the system? Positive 1.8 to get it to 0. That's what it's telling. No. This would be a reasonably stable system. I'm still not, but reasonably. Okay. I like example 5. I like example 5. Example 5 is a nice question. I think it's the last one. Yes, it is. Okay. Adam, what's example 5 asking me to find? Is it asking me to find work? What does it say for the hint? Dolp. So an electron starts out 3 meters to the right of a fixed. So here's my fixed negative charge. Yoink. I'll put a big negative there, and above it, all right, -5. You know what? I'm going to abbreviate microcoulombs. I was going to put the 10 to the -6 in. I'll do that in my equation. Where's the electron atom? How far? Okay, and then keep reading. Oh, okay, so it's moving towards. So I'm going to start the electron way out here, and I guess it's moving towards it. What's its speed when it's moving towards it? Oh, actually, let's do this. And I guess it's, what's its speed, Adam? Is that an initial or a final speed based on this question, do you think? What's V final? Sorry? Yeah, so here's what I think is happening. This electron is moving towards this negative charge. What's the charge on an electron, negative or positive? So like charges, you know what? It's getting repelled. It's slowing down, slowing down, slowing down, slowing down, slowing down. Apparently, there's some spot, let's say right about there, where it comes to a stop. And I think what this question wants me to find is that. That R, is that a final or an initial? Okay. I don't know if this is the best diagram, but I've got my brain wrapped around what's going on here. Any thoughts on how I'm going to solve this? Conservation of energy. How do I know? Did it ask how much work? No. Is there a change in height, change in speed, yucky curvy force? Yeah. So I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. Are any of these zeros? Oh, that's a bonus. Adam, what am I trying to find? Where is R final hidden in which of the 3 remaining terms? Okay, I would get this by itself. It already is. So now I'm just going to plug in what each of these equations is. This is going to be a half m v initial squared plus little k big Q little q over R initial. That equals little k big Q little q over R final. I could try and get the R final by itself. I don't recommend it. What I'm going to do is I'm going to turn this into one number. Then I'll get the R final by itself. So here we go. Let's plug in our numbers. A half, that's 0.5. M. What's moving? It's an electron. V, 4.6 times 10 to the 7th. Don't forget the squared. Plus, little k. If you want to write out 9 times 10 to the 9th, you can. If you want to abbreviate it with little k in your work, I'm good with that. Big Q, that was -5 microcoulombs. Little q, it's an electron. Okay, make sure you know where we're finding these numbers, right? They're on that reference sheet. All over, and I guess our initial is 3. That equals K big Q little q over our final. I think I'm going to evaluate the first expression, then evaluate the second expression, then combine them. This is, again, where my love for typing everything in one step kind of dies an ugly death. 0.5 times 9.11, negative 31, times 4.6 times 10 to the 7th. Don't forget the squared, Mr. Dewick. And you know what? I'll carry extra sig fig. Every sig fig, it's 6 of them. So 9.63838 times 10 to the negative 16. 9.63838. Is that what you folks got as well? Yep. And then the second term, 9 times 10 to the 9th, negative 5 microcoulombs, negative 1.6 microcoulombs divided by 3. Look for typos, Mr. Dewick. I said negative 1.6 microcoulombs. It's negative 1.6 times 10 to the negative 19, Mr. Dewick. But I typed it right, even if I said it wrong. And I get 2.4 times 10 to the negative 15. That equals little k, big Q, little q over r. All right, let's combine these. No, am I wrong? (9.63838) times 10 to the negative 16 plus answer button. The nice thing is I'm getting a positive answer, which is good because I want to get a positive radius. Am I wrong? I see people staring. Have I made a typo? Where did I make a typo? Oh, I wrote it wrong. Okay, but I've typed it all right, I think. Yes? I hope. 9.63838. 9.63838. 9.6. Yeah, I think I'm good. Yes? Okay. I get 3.363838 times 10 to the negative 15. I get 3.36 times 10 to the negative 15. I didn't write down everything because I'm just going to use my answer button anyways. That equals K big Q little q over R. Our final. Is that okay, Manav?
Yeah, I just forgot the square.
Okay. How will I get the R by itself? What? New dance? Hip hop? Oh, no. What? Stuff moves diagonally. So I'm going to say to myself, you know what? The RF ends up there, and the answer button is going to end up there. So now I think I'm good. Final, it's going to be little k, negative 5 microcoulombs, negative 1.6 times 10 to the negative 19, all over my answer button. 3.3 times 10 to the negative 15, 3.36, that thing. Don't want to mess this up because then I lose my answer button. Negative 5 microcoulombs, negative 1.6 microcoulombs. Do I want my radius to be positive or negative? What's any radius always going to be? Positive. Are all my negatives canceling? That's a good sign. That means I'm probably doing this correctly. Divided by answer button. I also know the answer has to be less than 3. Why? Look at the picture. Okay. I have no idea what this is. I hope I made up good numbers. Let's find out. 3, 2, 1. Whoo! You get 2.14. So it gets within 2.14 meters and it turns around. Okay? The flip side of this would be I could start close with the charge moving away but being attracted, and I could basically say how far away does it get. That's like throwing an object up and asking how high does it get, but you'd have to use cosmic potential energy. If it was a rocket, you'll use electric potential energy for here.
It's negative 2.44.
What? No, you can't get negative. You have to get a positive. There's no way you can get a negative radius. You missed a negative somewhere then. Okay? What's your homework? Two is good. 3 is good. 4 is good. 5 is good. And I'm going to be giving you a bunch of questions from the ultimate review. Okay? So bear with me while I go find a copy of my ultimate review. So you are now capable of doing from the ultimate review number 2. Really, you can do anything that doesn't mention volts. Tomorrow's lesson, voltage. 5. 10. 11, 12, 14, 16. I like number 16. I like number 16. I like number 16. 16 is a nice question. 17. 21, 24, 25, 27. 27 has some teeth. 27. The 2 on my keyboard sticks. 30. 31. 33. 34. 35. 36. 37. 41. 46. 47. 52. So we've been talking about electric potential energy, how much energy is stored by charges. There's a fair bit of energy that can be stored by charges.